Welcome everyone to Chapter 6, Mechanics of Metals. This is a two-part lecture. It'll cover kind of the introduction to the kind of elastic regime. We'll go into the plastic regime as well. So this video will cover the two lectures on mechanics and metals that are in the syllabus. So as usual, we start with the why should a mechanical engineer care? In the case of mechanics of materials, this is something that is pretty much everywhere, right? I like the example of bridges. You have many different materials all coming together in order to, facilitate, something like this. And the reality is that the actual bridge's functionality relies, very heavily on understanding the actual mechanical properties of the materials that are made of it. For example, if you have something like steel, it's strong. So why are a lot of the pillars that actually hold up the bridge, why are those made out of something like concrete a lot of times? What you'll quickly find is that mechanical properties, in a static environment are one thing, but then those same properties in a dynamic, environment that actually contains things like temperature differences, corrosion differences, those things can all ultimately affect the mechanical properties as well. So it's a very complex structure property relationship. So, when you think about bridges, again, you have this scenario where a lot of times they're over water. So if you make the pillars that actually hold the bridge up out of things like just pure metal, you're going to find that they rust very quickly, and then that corrosion onset ultimately degrades its mechanical properties. So you want to find a material that has similar mechanical properties, but ultimately doesn't have the same corrosion problem. So concrete or steel reinforced concrete is kind of your substitute. And then there's also the cost aspect that goes into this. So but again, why should a mechanical engineer care? You're talking about extremely large application spaces where you would be interested in something like the mechanical properties. So for the purpose of this lecture, we're really going to focus on this idea of mechanical deformation and how does that affect the properties of the material, and somewhat discuss what deformation actually means, in the context of the structure side of the material. The main theme of this lecture is that we have two regions, when you deform a material via some sort of mechanical force. The first is the elastic region, and the second is the plastic region. And from this stress-strain relationship that we're looking at here, the region to the left, this kind of linear region, is your elastic region. And pretty much everything else, once it enters that nonlinear region, is the plastic zone. And we'll notice that as we kind of move along this stress strain curve, we can even see these little inserted images that show snapshots in time. And you can see that there is a structural change that occurs, and we will talk about those changes throughout this lecture. But again, so just to reinforce this idea, the linear region is your elastic region, and the nonlinear region is your plastic region. So we're going to start the first half of this lecture focused on the elastic region. So the concept checks, obviously, we're not in class right now. The way the concept checks work, you're welcome to participate in them, but we'll kind of just stop here for a second, read the problem. Again, you're welcome to vote if you want to, but then we'll pretty much just jump right into the answer. So the question here is, do you think all materials can have a stress strain curve that looks like the one below? And what I mean by the one below specifically is that there is a unique elastic and plastic region. The answer is it kind of depends. I know it's not a great answer, but as most things in material science, it really does depend very heavily on the actual specific conditions that we're talking about. So, for example, these stress strain curves are kind of snapshots based on the external conditions. So what temperature was it at? How humid was it? Anything like that. What pressure was it under? And the stress strain behavior can ultimately change depending on what those conditions are, and we'll talk about those. Another aspect of this is, what really counts as a new material. If the material is corroded beyond belief, is it really the same material anymore, or is it, maybe some oxidized version of what you started with. So, is it possible to create a stress strain scenario that looks like this for pretty much all materials? Pretty close. But again, you have to change the conditions that it exists within. So when we're talking about different types of mechanical loading, so this is the type of force that you can apply onto the material. The two simplest are compressive and tensile. So compressive is you're applying a force and essentially making it smaller somehow, and a tensile is the opposite. You're applying that force but making it larger. So the idea, kind of physically, is you're crushing something, making it smaller, or you're kind of pulling it apart, and that's your tensile force. Two more complex, slightly more complicated ones, but still relatively simple, is this idea of shear. So you apply a force onto the material, and instead of just pulling it, either negatively or positively along one direction, you're kind of changing multiple directions at once. So I equate this to, say, maybe taking a box and turning into some diamond shape. The volume doesn't really change necessarily, but the shape does. Intorsional, so you're applying a rotational force onto the system, so you're getting a rotational structure change. So, in order to really understand all this, we also have to understand what the concept of stress even is. And in particular, engineering stress. We'll talk about different types of stress throughout this lecture. But think of it this way: you're applying a force over some area. That's it. It's similar to a definition of pressure, but stress is kind of a more universal force per area, whereas pressure is kind of specific to certain instances. So in some way, you can think of this as how much force does a material feel over a given area. So in this diagram here, you kind of have this force vector, approaching down in the material over some area A. And don't think of it as the force is being exerted on the kind of point of the arrow. Think of it more as this force vector that's being applied is being applied uniformly over the entire area A. And then that force will ultimately cause the material to change, and this is where the strain comes from. Strain, at least in the context of something like tensile or compressive, is fairly straightforward, right? You apply a force, the material changes along one direction, so you can simply measure the strain as the change along that direction. So your current length in this scenario versus, or with relation to the initial conditions. So because of that, what you'll end up finding is that you have a negative and positive strain variant. The case of compressive, the negative strain is implying that the material has gotten smaller, and then in tensile, the positive implies that it's gotten bigger. That is purely due to convention. You could flip your L naught and Li and redefine this somehow, but it's the standard convention is that negative strain means it got smaller and positive strain means it got larger. Now shear stress or shear strain in particular is a little bit different, in part because the material is changing shape along two directions. So you really don't have the same kind of simplistic length-based change that you did in compressive and tensile. So here you would define the strain really as a function of the angle that the material actually underwent that change in shape. So the tangent of that angle is how you define the strain. The stress is going to be defined in pretty much the same way. It's still a force that's being applied over an area. It's just leading to a different physical change within the material. Now, the definitions that you just saw are really defined for the case where the stress or the force that's being applied is acting either in parallel or perpendicular to the actual planar faces of the material, so those outside faces. If you want to do this for an arbitrary geometry, your kind of definitions are down there, defined with regard to the angles that the stress is actually being applied. Now this is relevant, and why is it necessary even? You may, for example, apply a force kind of diagonally onto a material. It's not perpendicular to the material. So how that force actually gets distributed within the system may change, right? If you're applying it along one of those planar faces, all of that force is being distributed evenly into the material because it's perpendicular to it, right, or parallel to it. Um, but in the case of some either non-zero or not 90-degree force that's being applied onto that material, the force will get distributed throughout the material in different ways, right? Maybe it's partially maybe I applied a force and 80% of it went to the tensile force and 20% of it went to a shear force. Um, and again, that depends entirely on the material, what its structure is, and the actual angle that you applied that force at. So one important aspect of these stresses and strains that we're talking about is the ability to actually quantify that relationship, so that stress strain relationship. This is done in a couple of ways, but it's almost always done through this idea of a modulus. And in reality, the modulus is just a slope, but it's a slope under different scenarios. So the elastic modulus, you may also hear this as tensile modulus or Young's modulus. It's all the same thing. But this is a really the slope of your stress strain curve when you're doing tensile or compressive deformation. Similarly, shear modulus, this is going to measure deformation of shape, specifically at constant volume. So we talked about this earlier. And then finally, bulk modulus, this is measuring volume definition. So again, that stress strain relationship under volume deformation, specifically isotropic volume deformation, meaning all of the material is changing its volume at the same rate. So this is essentially the equivalent of a box kind of getting bigger, but it's remaining a box. So all those axes relationships are the same. If one side of the material is changing its volume deformation faster than the other, then in reality you don't have one bulk modulus for the entire material. You would have to break the material up into segments, and you would have a bulk modulus in this portion and a bulk modulus in this portion. And the reason for that is because the fact that the material is changing in different ways depending on where in the material you were means that there are different structures within the material. So you would need a bulk modulus for each structure that you were actually looking at. So let's talk about this first for the scenario where we have this tensile compressive deformation. So this is what this relationship looks like. If you remember back to the very beginning, we talked about how the elastic region was that linear region. So that means that our relationship is really just a y equals mx plus b, which is what you see here. Your y is your stress, your m is your modulus, and your x is your strain. There is no b because the y-intercept is 0, so it's 0 stress, there's 0 strain. But that's really what this is. So this comes from just a simple y equals mx plus b. But again, if you look at something like brass versus tungsten, you'll quickly find that tungsten has a nearly 4 times larger modulus of elasticity. What this means, again, in principle, is that you need to supply 4 times the amount of force on tungsten compared to brass in order to induce the same strain. So that's what this means. Again, you apply a load on the material, and the slope within that elastic region is your elastic modulus. You will notice that this plot on the left has kind of an up arrow and a down arrow with a load versus unload. Again, you're in the elastic region, so what that means is that you apply some force on the material, you're straining the material, but once you remove that force, the strain would essentially go back to 0 within that elastic region. So it recovers all of that deformation. However, once you enter the nonlinear region, so that's the plot on the right, any of that deformation is permanent. That is your plastic region. And we have, again, you can measure the slope within those regions. Obviously, it's a smaller window that you can measure the slope in because it may be changing at different rates. And it still is measuring the same thing, right? It's how much, what is the change in force needed to induce a given strain. But obviously it's changing at a different rate than you would within the elastic region. So another question. So thinking back to the plot of force versus distance, how do you think the slope of this curve affects the elastic modulus? So feel free to answer the QR code if you're interested. But the answer is that a larger slope equals larger change in force equals stiffer material. So that's really the kind of portion on the left of this red line where you kind of cross that 0 point and then you kind of dive down into the negative region. So essentially, if you're pushing atoms closer and closer, if that slope is larger, that means more energy is needed to actually push those atoms closer together, which means that you would need to apply a larger force in order to actually facilitate pushing those atoms closer together. So that ultimately leads you to a stiffer material. Interestingly, though, if you actually look at this, so it's a similar plot to what we showed back in our bonding lecture, but the elastic modulus is essentially proportional to the slope of the force, within, prior to that equilibrium bond length. If you don't want to do this past the 0 point, because essentially the atoms are just getting further and further apart, so they're not really interacting anymore. But interestingly enough, the slope of this line is also the stress. So what you'll find is that the first derivative of energy with respect to distance is the force, and the second derivative of it is actually the stress. So again, shear modulus, similar concept. It's still y equals mx plus b type relationship, but now the difference is that the stress and the shear or the stress and the strain are both shear variance, and then the modulus is obviously capturing that specific relationship. Bulk modulus is slightly different. Here it's more about this product between the initial volume and the change in volume. That gives you a sense. It's kind of that ratio between the two. You can also arrive at bulk modulus by measuring energy as a function of volume. And essentially the bulk modulus would be the slope at that kind of energy minimum. So that is another way to access bulk modulus. Poisson's ratio is a kind of non-moduli other mechanical property, but it's also incredibly important. What does it actually do? So if you apply a force to the material, you're straining the material maybe along the z direction, maybe it's a tensile force. But rather than the, say, cross-section remaining constant, the cross-section can change. So what that means is that now you have a strain in, potentially all three axes. And essentially what Poisson's ratio does is it measures the change in one of those, X or Y dimensions, but with respect to Z. So you can see in the definition down below, strain of X over strain of Z, or strain of Y over strain of Z. So again, you're measuring the change in either that X or Y direction, but you're doing it with respect to the actual tensile direction, which in this case would be the Z-axis. So there's an example here, example problem that you can solve. So essentially you have a tensile stress that's being applied to the cylindrical brass rod, the diameter, and what you want is the magnitude of the load required to produce a given change in the diameter. If you know the deformation is entirely elastic, you have all your terms, so feel free to solve this on your own and then kind of skip ahead. So the first step that you need to do is recognize that ultimately what you really want is the strain in Z, since this is a tensile force that's being applied onto the material along that direction, and you don't have that. So what you do have is you have a change in X, which is, kind of your cross-section diameter difference. So you can solve for that and then use Poisson's ratio because you know it for brass in order to solve for the strain in the Z direction. You can then solve for the stress within that Z direction. So along that tensile direction, you can solve for that stress by using the elastic modulus coupled to the strain in Z, giving you your stress. But ultimately, what we wanted was the magnitude of the load, not the stress itself. So that would be force. So you need to understand that this is a circular area, and because that force is being applied perpendicular to that plane, that's where the force actually comes from. So that's why your area in this case is the area of a circle, and you plug your values in and you get your final solution. Another important aspect of this is that elastic properties, mechanical properties in general, they're not constant, right? They depend on many things. Temperature is an easy one to visualize. You heat it up and obviously it's changing its structure. So in this case, you could have tungsten, it drops a little bit from, negative 200 to 800 C. Aluminum sees an even larger drop. Part of the reason for that is that, 800 C is not really close to the melting temperature. of tungsten, whereas with aluminum, it's beyond it. So you may see a larger drop off at the lower temperatures for materials as you're approaching that actual melting temperature, whereas for materials that you're not even halfway there to the melting temperature, you're not going to see as much of a degradation. This is important because what it means is that you're going to see a larger degradation the closer you get to something like melting temperature. So another important aspect of this that we haven't really talked about yet is that there's a time dependence to all of this, right? Everything we've talked about up to this point is kind of this ideal elastic scenario. You apply a stress, there's kind of this static change in strain, and it's not really changing at all. And then when you remove the stress, the strain essentially, if it is purely elastic, just goes back to zero. The reality is that this is not necessarily true, right? There's usually an actual time dependence aspect. So this would be your linear viscoelastic and anelastic. We'll talk about other types of time-dependent behavior, particularly when we get to things like polymers. But if you look at the anelastic case, this is a small effect. So, think of the y-axis here is you've applied an initial stress onto the material. That stress is constant, but you're kind of changing the strain as a function of time. So in the case of the anelastic, you apply that stress, you have this kind of small change in the strain as a function of time, but eventually it kind of plateaus. And then when you remove that stress, it takes a little bit of time to kind of restore all of that strain that was induced. It's not this kind of immediate jump back down to no strain at all. And the viscoelastic case is, there's a much larger and even constant change in strain when that stress is applied, and it never really plateaus. And then when you remove that stress that you've applied, it's still kind of similar to the anelastic. It takes a little bit of time before it eventually plateaus off. But the important part here is that in the viscoelastic case, you didn't recover everything. So you can think of this as a form of plastic deformation, but we'll talk more specifically in polymers about what viscoelastic actually means structurally, when you apply a stress to it. So now let's move into the plastic region. Plastic region can be broken up into a few different zones. The first is, you've left your elastic region and you're kind of pushing yourself towards this M point or tensile strength. We'll talk about it later. That is where you're kind of seeing a uniform deformation within the material. Past that point, you're getting localized deformation. So that's why you're seeing this kind of hourglass shape start forming in the pictures. That essentially means that the stress is concentrating within those specific points. And what you're actually seeing is a phenomenon called necking, where, again, that stress is highly localized to a specific region, and that is the region where the material will ultimately fail. And that's failure is the point F, or fracture point. So that's kind of, what I just said. The beginning of the plastic region, the material is actually getting stronger. And then once you've reached that kind of maximum stress that you can handle, the strength decreases, in part due to this localized deformation that is making the material, in principle, weaker. So the first important aspect of the plastic region is the yield strength. So this is kind of the stress required to facilitate plastic deformation. So in principle, again, you start off in your elastic region, that's your linear, and you may have this kind of slightly elastic plus plastic buffer zone where there's a little bit of plastic deformation happening, but maybe some of it's recoverable, but not all of it. But then eventually you pass this point sigma y, or your yield strength, where anything past that point, there is no elastic deformation anymore. It is purely plastic. And one way to estimate this yield strength is, you kind of take a strain of around 0.002 and 0.005, and you figure out, draw a line that has the same slope as your elastic region. Where it intersects your stress strain curve is a rough estimate to what your actual yield strength would be. So an interesting concept check is what happens when you have this scenario where you're kind of increasing in your linear region, and then you hit this upper yield point, and then a quick drop off to a lower yield point, and then some oscillatory behavior before you pick up again and enter into a nonlinear region. And the question is, given that kind of complicated yielding behavior, what do you think the yield stress actually is? Is it at the upper yield point, or is it at the lower yield point? The answer is surprisingly the lower yield point. And the reason is, if you think back to what yield strength is, it is the point in which there is no longer elastic behavior, right? It is the transition between elastic and plastic. And there is no requirement that that transition point happen at the maximum stress that can be, essentially met prior to plastic. And that this is an interesting caveat in that you can actually have scenarios like this where you can sustain actually a fairly large stress, but then something happens in the structure of the material that you see a drastic drop off in the stress that can be handled. And then it's only after that drop off do you actually see permanent damage to the material. We'll talk more about this when we get into failure and even strengthening of materials. But it's an interesting phenomenon here. But it's important to remember that what yield stress is actually measuring is that kind of transition period between the elastic and plastic region specifically. So this is kind of just a recap of what I just said. A key to this, though, another key piece of information is that kind of parallel offset line we just talked about to estimate the yield strength. You can't really use it here because obviously there's not a continuous stress strain behavior. There's kind of a discontinuous behavior at that upper yield, lower yield kind of transition region. So tensile strength, another term, that is that M point, that is your maximum stress, engineering stress specifically, that the material can tolerate while under tension. You will also have equivalent of these compressive strength, shear strength, all of those things. It's still kind of the same theme here that it's, the stress strain curve is specific to a type of strain, a type of force being applied. So in this case, because we're talking about a tensile force, it's called the tensile strength. So the tensile strength kind of represents our transition between this uniform deformation and concentrated deformation or localized deformation. So prior to the tensile strength, you're getting uniform, homogeneous stress applied throughout the material, which is making it stronger. And we'll talk later on in strengthening about what the actual mechanisms behind that are. But once you reach that M point and transition beyond it, you're getting localized stresses. So the stresses are building up in certain spots, getting this necking behavior, at least in a ductile material, until eventually you hit that fracture point. So we're going to do another example here. There are two questions that you need to solve. The first is the modulus of elasticity. So given all this information, figure out what the tensile modulus is. And the second is the maximum load that this cylindrical rod can actually sustain if you have an initial diameter of 12.8. So there's a couple of little subsets here. Note that the 150 MPa 0.0016 is pointing to a point within the linear region of the subplot, and the subplot is just a kind of zoomed in region of the very beginning of the much larger plot. Again, that A point there, A345.06, is literally pointing to the A on the plot. So modulus of elasticity. So we know that that's the slope within the linear region. So you can literally just pick that point that I had added onto the diagram, that 150 and then 0.0016. And again, the second point can always be the origin because it's the slope it's a linear region. So you can pick the origin always and then use those 2 points to get your elastic modulus. So once you have that, another important aspect of this is we want the force. So that's the second question here. That the original diameter is 12.8 millimeters. So again, the key here is understanding that what we're really looking for is this idea of a maximum load. So that's your tensile strength. So that is why the stress that you can actually plug in here is that 450 times 10 to the 6 newtons per meter squared, which is your 450 megapascals. So it's important that you be able to read the various regions of the stress strain curve, then understand, what the terminology is. Maximum load, is tensile strength, load is force. It's very easy to get these things confused, but these practice problems, and especially the practice problems and homework, are going to help you, be able to differentiate these things. So another important aspect is ductility. So this is essentially measuring the strain. So this is a strain-based property. So ductility is measuring the amount of plastic deformation sustained at the fracture point. And, there's two ways to do this. The first is strain-based. So that's literally just, the strain final minus strain initial divided by strain initial times 100, right? That's, you're measuring the strain of the initial and the final. And the second is cross-section based. So this is particularly useful, if you have something like that cylindrical rod and its cross-section is actually changing, so you can measure a reduction in area, essentially. Important to note, though, that brittle materials are materials that, their ductility is small, so they really didn't sustain any plastic deformation prior to that failure point, whereas ductile materials can sustain a significant amount. It is important to understand as well that brittle and ductile have nothing to do with a tensile strength. It is purely a strain-based property. Resilience is kind of the next important one. This is more of a force or energy term, specifically within the elastic region. So it's essentially the area under the curve of the elastic region. Or particularly up to the yield strength. Again, there could be a slight buffer zone in the nonlinear. So it's physically, think of it as how much energy or force the material is actually going to absorb during that elastic deformation. So a material that is resilient is one that can absorb a very large amount of energy prior to entering that plastic region, which is good, right? I guess in certain things, in certain applications, it's good. If you want the material to not have plastic deformation, you would want a resilient material. However, there are materials that you want them to fail pretty quickly, right? Think of a material that you want that material to break in order to, say, stop something. And an easy example of this is from electronics. Think of a fuse, right? There are many instances where, you don't want, say, a large amount of energy to be transferred onto something else and cause damage to that other piece, other component of your system. So you have a material that is kind of there to absorb that and fail so that the energy is not transferred to something else. So that would be a material that would not be resilient, but also has a very useful application. So since we're in the linear region, we have a pretty nice little heuristic relationship between the elastic modulus and the resilience. So this is particularly useful if, for example, you are trying to find the resilience, the yield strength, and the elastic modulus. It gives you a nice, easy way to kind of estimate what the resilience would be without having to have an actual resilience test or have this kind of continuous stress strain relationship. You may only need really 2 points or maybe even 3 points, your yield strength, your origin, and a point along the elastic region to get your elastic modulus. Fracture toughness is now the area under the curve up until the stress strain point. So this kind of is where the idea of a tough material comes from. So this would be something that has both strength and ductility. So materials that are very strong but very brittle are not going to be tough, whereas materials that are extremely ductile but not very strong are also not going to be tough. So your tough materials are going to fall somewhere in the middle. They're materials that have fairly high things like tensile strength, but they're also fairly ductile materials. And as a reminder, all of this can change as a function of temperature. So this is an example where you essentially are starting with a material that is fairly ductile, but is not very strong at 25 C. And then you cool it down to minus 100 C, and it's, you've 1.5 times the tensile strength potentially, but you have lost a little bit of your ductility. But if you cool it down even further to minus 200 C, you've gained a significant amount of tensile strength, perhaps maybe even upwards of 4 times, but you've made the material incredibly brittle. So there are structural changes that are happening inside the material that are ultimately leading to that. And that's an important aspect of this, right? Is that all of this is actually happening not just because temperature is some mystical force, but because the temperature is changing the structure of the material somehow. So there's another concept check. As the engineering stress goes down, is the material getting weaker? So specifically, once we've reached that tensile strength point and we've transitioned past it and we're kind of driving towards failure, we're seeing the material is in principle getting weaker, right? It's sustaining smaller and smaller stresses in order to keep facilitating larger strains. But is the material actually getting weaker as that engineering stress goes down? And the answer is no, it's not. It's actually getting stronger. And this is a kind of counterintuitive thing to discuss, but if we think back to what our definition of stress actually is here, in specifically engineering stress, it's forced by area, but specifically the initial area. And this may apply in work rather well in the scenario where we're in the elastic region and even somewhat into that initial plastic zone. But as that area, specifically that cross section, is changing, and it changes significantly after the tensile strength point. In fact, it's not even potentially the same shape anymore, right? Once you have this necking region, you have this very complex topology that could be happening within that failure zone. So the area is nothing compared to what it was in the beginning. So what is potentially happening is that the kind of stress-strain relationship with respect to the initial area could potentially be significantly underestimating the amount of stress that would actually be needed to further strain the material. So this is just kind of a repeat of that. So that brings us to this idea of engineering versus true stress and strain. So in engineering, both of these are a reference to the initial conditions. So you can think of this more as a relative value. So your engineering stress and strain are relative with respect to the initial conditions. Whereas this true stress and true strain are more, you can think of them more as an absolute term. So in the case of true stress, it's still the same definition, right? It's stress is force per area, but specifically the area is now the area at snapshot I, so a point in time rather than the initial. So this allows you to have a better estimate of what the current area of your cross section is, or whatever plane of the material where the force is actually being applied. And true strain is still kind of with respect to the reference. You do have that kind of relative value of current with respect to reference, but now it's a log-based relationship rather than just a basic linear relationship. So that leads us to this. So we have three curves here: engineering, which is what we've already talked about; true, which is the new value, and this corrected. So what you'll see again is that all three of these are effectively the same within the elastic region. That's because the cross-section area is not really changing with respect to the initial conditions. And even once you enter into that plastic region, that non-linear region, there's still a significant period of time where that area is not really changing that much. So the engineering in true values are going to be very similar. But once you start seeing a significant change in that cross-sectional area, that's where you start seeing that deviation between the engineering value and the true value. And that M prime is what you would ultimately call your ultimate tensile strength as opposed to just tensile strength. In principle, it gives a much better estimate of what's actually happening. However, the true value is actually overestimating the amount of stress that is actually happening, and the reason is that the area is more or less considering a simplified version of the actual topology. So it's what happens if you start off with a square, a square area within your cross section. But by the end, you have some weird jagged topology that is very complex. Area is not necessarily easily quantifiable anymore, but you're still using, a simplified metric to gauge the area. What this corrected curve is doing is it's accounting for that, right? It's accounting for the fact that you could potentially have a very complex stress state occurring within that failure region. So it accounts for the overcorrection that the true stress definition is going to have in it. So let's do an example again. So the first, this is a problem where you have a cylindrical rod, its original diameter, and it is tensile tested to fracture. So that means we did a tensile test and it ultimately failed. Well, the material failed, not the test failed. And we know that it has an engineering fracture strength of 460 megapascals, and we know what its cross-sectional diameter was at fracture. And there's two things you need to do. The first is figure out what the ductility is in terms of the percent reduction in area, and the second is the true stress at fracture. So you have a couple of functions, so you'll take a minute to do these on your own. So to solve for the ductility, we already have the values. So, the only real thing that we need to understand is that it's a cylindrical rod, so we need area of a circle. And the rest of this is simply plug and play. So we find that there's a 30% reduction in the cross section. The second piece is the true stress at fracture. And what we have is the engineering fracture strength. The problem is that the engineering fracture strength requires an engineering stress relationship, right? So that you need to use your initial area in order to get that force. Now, the force will be the same force, but the actual measured value will be slightly different. So the measured stress value could be slightly different. So again, we have our initial area, we have our engineering fracture strength, we use that to solve for the actual force that will be encountered. And then we plug that into this kind of second piece, same equation, but this is the true stress equation. We use our final area in order to solve for it. And we use that to get our true stress at the force that is applied during that fracture point. Interestingly, you will notice that the true stress gives you 660 megapascals at fracture, whereas the engineering fracture strength was 460 megapascals. So a nearly 200 megapascal underestimation by the engineering fracture strength. All right, let's talk about elastic recovery. So we know that if you're in the elastic region entirely, you'll recover all of the strain that was applied to the material. However, once you go into the plastic region, you can still recover things. It's just you won't recover all of it. So this is an example. You have that initial yield strength. You kind of go past that initial yield strength, that point D, and then you remove the load on the material. The material will still have some form of elastic recovery, but again, it doesn't recover all of the strain that was applied. It is still somewhat plastically deformed because you entered into that plastic region. Interestingly, if you reapply the force onto the material, you now have a new yield strength, and it's that sigma yi. So essentially, you have to go back up to the stress that you encountered at that point D to further deform the material. And again, we'll talk more about this when we go over strengthening of materials. But essentially what you're doing is you're permanently deforming the material once you go past the initial yield strength. So you've created a structural change in the material that you now have to overcome in order to further strain the material. So each time you go through this elastic recovery process, once you've entered into that plastic region, you will have a new yield strength. So again, we'll talk about this in great detail when we go over strengthening of materials. But this idea of elastic recovery, you can use this to strengthen materials. This is what is known as strain hardening. So you can essentially apply force onto a material, strain it, but do it in a very controlled way. And you can actually make your material stronger. So just because you are permanently damaging or permanently changing the structure of the material does not necessarily mean that it is a degrading property. It can actually be a benefit to the material. So again, this is just a reminder, we have these stress-strain relationships, and these are really the four we're going to cover within this course. But each one of these occurs under a different loading condition. What's interesting about this is that everything we've learned up to this point, we've really done this for the case of tensile. Tensile and or compressive, it's, similar thing. But in reality, all of what we've learned can be applied to any of these scenarios. The specific stress strain relationship may be slightly different depending on if it's a torsional versus compressive. But this idea of there being an elastic and plastic region and transitions that happen and everything like that, it is the same regardless of which loading condition we're actually talking about. So hardness is another property that's of particular interest. Hardness is a little bit more difficult to understand, and I think because people want to, at least in the past, have wanted to, students in the past in this course specifically, have wanted to apply hardness to the total material. We'll talk about this more again during strengthening and failure, but hardness is a measure of localized. It's a local property, right? So I could have a rod of a material, and it could have 10 different hardnesses depending on where I look in the material. And you can think of it as, if I pick a specific spot in my material, what is its resistance to plastic deformation? In some sense, what is its local resilience, right? So rather than having a resilience for the entire material, you can instead have a resilience for specific regions of the same material. And there are many different ways that you can quantify this. Each one of them has their own kind of application. It depends on how the plastic deformation is actually being applied. That ultimately matters, right? Are you applying the plastic deformation at like a very specific point, like you have a steel needle essentially, and you're trying to drill it into your material, or are you trying to take a very large ball and just push it into the material, right? That actual mechanism of plastic deformation will be different, so that's why you have different tests for hardness. They're measuring different physical situations. And as you can imagine, hardness in something like tensile strength are absolutely correlated. So in this case, the x-axis is a hardness number for a particular type of test, a Brinell hardness test, and the y-axis is tensile strength. So if you have multiple materials, say you take cast iron and you make many different samples of cast iron, or you test it in various spots within your cast iron sample, what you'll find is that as the hardness goes up. So again, the hardness is that test to localized plastic deformation. You'll notice that a sample that has, an overall, say, larger hardness is going to have a larger tensile strength. And this makes sense, right? If the plastic deformation is occurring at a smaller hardness, meaning less energy was required to plastically deform it, then that would ultimately mean that the material is likely going to have a smaller tensile strength because it's just an overall weaker material. So another concept check. This one is an interesting one. Can a material both be brittle, both be ductile and hard? So feel free to answer this if you're interested. And the answer is why not, right? So it may take a lot of energy to sustain that plastic deformation, right? That's your resilience term. But that really doesn't have any indication whether or not the material is brittle or ductile, right? You can have a material that, like this example here with the material B, which is brittle, its resilience within that elastic region is much larger than the case of B prime, but it's a brittle material, right? So, in principle, is it possible that B was harder than B prime? Absolutely. But you would need a better definition of what specifically is ductile and what specifically is hard, right? You'll put some quantitative metric on it. But the real answer is why not, right? There's no reason that a material can't, have a resistance to plastic deformation and also be a hard material, and those would be things like your tough materials. So another aspect of this, when we actually come to the engineering side of it, is we want safe materials, right? When you're talking about mechanics, a lot of times you're talking about applications that have, direct interface with the general public, whether it be transportation, whether it be packaging, whether it be residential building, anything like that, housing. It's a lot of it is dependent on mechanical properties. So you need to design safe materials. There's a couple of ways you can do this. Design stress and safe stress are one of them. Both of them, they essentially have this factor N, and it's a safety factor. So, in the case of the design stress, what you're doing is you're saying you want the material chosen to have at least a yield stress of sigma D. So, what you're saying is, I have an actual yield stress that I'm confident in what I actually need. That's your sigma C. But in principle, maybe you actually, for safety reasons, you would go 3 times that number. So that's why the N is multiplying, is multiplied by that sigma C. And then safe stress, essentially the material chosen has a yield stress divided by some safety factor. So if I say, I'm confident that, the material that I want or by application that I need, maybe I need 1,000 megapascals, but for safety reasons, I want a material that is at least 5 times larger, than the number that I really want. So in principle, you would want that sigma y divided by your safety factor. So you would want materials that more or less have, 5 times larger than whatever value you wanted. I mean, in principle, they effectively do similar things, but there are different reasons why you would use one versus the other. Design stress is often used in practice because it's based on the anticipated yield stress that you would need for the application rather than specifically the yield stress of the material itself. So this is an important distinction here that if you already have the material in mind, maybe safe stress is a better way of doing it. But if you have more of a what I actually need in terms of a yield stress, then that sigma D of the design stress gives you a starting point to then go see what materials have, say, at least sigma D.